Fine. So spherical harmonics. Today we are going to talk about the spherical harmonics. What actually spherical harmonics are. Now these spherical harmonics actually are the special functions. Like we had other kind of special functions. We talk about the Bessel, we talk about the Legendre, we talk about Hermite, Legure, spherical Bessel functions, and some other functions also. Likewise, there are spherical harmonics, and these spherical harmonic functions are also the special functions. They are defined on the surface of a sphere, right? So they are defined on the surface of a sphere and are used in solving the partial differential equations. So let me write it here. Spherical harmonics are special functions defined on a surface of a sphere and are used in solving these partial differential equations. Okay, I will elaborate this in a while, but first of all I will give you some introduction about the spherical harmonics. What are actually the spherical harmonics and what is their importance and why does it arise actually. Okay, now just like spherical surface kya hai, just like we have the periodic functions, and you know what are the periodic functions, which are which keep on repeating after the regular intervals of time or regular intervals of time or regular intervals of the frequency, whatever we have. So like we have the periodic functions, they are defined on a circle and can be represented as a sum of sines and the cosines. So that is what we call as a Fourier series. So you have not gone through the Fourier series yet. That is in the second semester. So like we have the periodic functions that are defined on the circle, we have these special functions, spherical harmonics, that are defined on a surface of a sphere, and these are actually used in solving the partial differential equations. Now, how we denote these spherical harmonics? These spherical harmonics are actually denoted by, they are denoted by this y, l, m, cos theta, phi. Yani these are actually the functions of theta and phi. I will come to this in a while. So now let me just go back to your previous thing which you already know. Since we know that from the separation of the variable, when we actually separate some differential equation, like we have the Laplace equation or Helmholtz equation and the Schrodinger equation in the spherical polar coordinates, that you have done. So solving separating those differential equations, चाहे Laplace आप ले लो, चाहे आप Schrodinger equation ले लो, and even Helmholtz equation. Helmholtz equation, when we separate them into spherical coordinates, you know that जहाँ पे मैंने, if psi is a function of this r, theta and phi, we write this as r function of r, this theta of theta and phi of phi, right? This is how we actually, then we substitute this thing instead of psi into the original differential. खासकर हमने Helmholtz equation वहाँ पे लिया था, right? So now this particular function actually contains, I will come to this in a while, huh? This is an elementary treatment what is actually that, but first let me try to give you an explanation what actually are the special functions, some introduction about the spherical functions. Now as I said ki these spherical harmonics are actually the special functions. This thing I'm going to explain it step by step, this thing, and that is an elementary treatment to these spherical harmonics, and you will learn from that. But first try to concentrate here. As I said ki these are the special functions and they are defined in a sphere. So now this, it is denoted by YLM. Actually YLM is the product of these two functions, theta and phi function. Okay, so that's why I write it as a function of theta and phi. So where this L is an orbital quantum number and this is a magnetic quantum number. Usually you are going to use this in the in a problem in quantum mechanics, the hydrogen atom जहाँ पे जिसकी हम बात कर रहे हैं. So this M actually is an magnetic quantum number. This L is an orbital quantum number, right? ठीक है. So this y is a function of theta and phi, यानी this theta is actually is a function of L only, but this phi जो है, sorry, phi is a function of L only, but this theta is a function of L and M. ठीक है. Now for spherically symmetric problems or spherically symmetric potential, अगर for example for spherically symmetric potential, spherically symmetric potential function. Potential function we actually denote it by V and is a function of R, and V is a function of R. The solutions of this theta and phi, which are called which are the angular solutions, they are actually solved once, and we take the solution which is equal to the product of this. So the solution, that is theta into this phi. Okay, the product of these two solutions of this theta equation and the phi equation. Now you as I was saying, when we actually separate the Helmholtz equation into three, you know that you get three different equations, one in R, the other in the theta, and other in the phi. Okay, so the solution to this theta equation and the solution to this phi function, this phi differential equation, when I take the product of these two particular functions, so that is what we call as a spherical harmonics. So this spherical harmonic जो मैं ऊपर लिख रहा हूँ y l m theta phi, it is actually defined as a product of these two functions. एक तो theta, which is a function of m and l, L yani orbital quantum number, and m, which is a function, which is a function of theta, and the product of this phi. Phi is a function of this m, magnetic quantum number only, phi of phi. So this spherical harmonic is actually the product of the solutions of these two functions. Theta's equation is the solution to the theta equation and the solution to a phi equation. Now from that particular difference, you just go through the through that particular lecture जहाँ पे मैंने Helmholtz equation को आपके this separate them into the spherical coordinates, जहाँ पे spherical coordinate में. Now the solution to this phi equation, it is always given by phi of m of phi, it is given by some constant a m and e to power I m phi. It is given by this. The solution to this phi equation, असल में अगर आप वहां पे देखोगे, the equation is like d2 phi by d phi 2 is equal to some a into some term here, phi m phi or something, m phi, this particular equation. Yani this is the solution. When you solve this particular differential equation, you will get the solution like this. And similarly, the solution to this theta equation, theta, which is actually a function of this orbital quantum number and the m theta of theta, it is always given by some constant, normalizing factor actually hota hai. This constant also depends upon the b and m, and we have this PLM cos of theta, associated Legendre function. That's why I told you last time, go through this associated Legendre function. Again, I'm going to just go through these things. We will obtain some of these spherical harmonics for the different values of these constant values. Okay, so now what actually, how we will, the solution to this phi equation is this, the solution to this theta equation is this, and you know that the spherical harmonic is defined as a product of these two functions. So I can write down this spherical harmonics then as, I will write down this as am dot this blm, and I have e to power I m phi, and plm cos of theta, cos of theta. So this is actually this is a spherical harmonics. Now taking the product of these, I will represent it by some another constant, so that I will represent it by the c l m plm cos of theta e to power I m phi. Okay, so this is actually, this is a spherical harmonics. Now the values of this c, the constant clm, can be obtained or can be concluded by the normalizing condition. So what is the normalizing condition? The normalizing condition is to find out these constant values. See, the normalizing condition is like, let me write it here. It's like we have theta running from 0 to 2 pi. This is for theta running from 0 to 2, no, not 2 pi, 0 to pi, and phi running from 0 to 2 pi. This is pi only, 0 to pi. Then we have this y l m theta of phi, and you know we are taking its complex conjugate star, and then y l m, which is again a theta, function of theta and phi, and d theta d phi, d theta d phi. Yani the values of these constants clm can be calculated using this normalization condition. We have obtained the normalization condition for the Legendre polynomial. Similarly, we can find out the Legendre this orthogonality condition or the normalization for this Legendre polynomials by calculating the normalization condition. This is a normalization condition. Normalization condition. Okay, normalization condition this. So when once we find out this CLM, I can find out this different spherical harmonics. PLM cos of theta, I can obtain corresponding different values of M and L, and similarly I can find out these things. Now again, this constant, I will show you an elementary treatment to find out these constants. But before going to find out the elementary constant and how we find out the different spherical harmonics, I'm going to just repeat it once again for just those who have joined late. Now, as I said, these spherical harmonics actually are the special functions, and they are defined on a sphere and are used in solving the partial differential equations. It is actually when we have, for example, अगर हमारे पास Helmholtz equation है या Laplace equation है या Schrodinger equation है, when we separate them into spherical polar coordinates r, theta, and phi, we are actually getting three different equations. One for this radial part, another for this theta function, and r for this. Then the solution to this theta equation and to this phi equation, the product of the solutions to of this and this, we call them as a spherical harmonics, and we represent them by ylm theta phi, which is a function of theta and phi. Now what is why it is so? There is a reason for this, because जब हम hydrogen atom problem solve करते हैं, so we derive actually three different equations there also. One is for the radial and other two for other theta and phi functions. Now the theta and the phi functions जो उसमें हैं, they are independent of the energy and this potential E and V. They are independent of energy and one. Only the radial part जो आपका है, that depends upon E and V. So radial part जो उसमें है, radial equation, that actually depends upon your potential energy as well as the potential energy. ठीक है? Okay, so the product of, so then the solution to this particular function, this phi equation, is given by e to power I m phi this thing, and the solution to this theta equation is given by this in terms of the associated Legendre functions. The product of these two solutions is what we call as a spherical harmonics. Okay, now let us try to find out the elementary treatment, how we can find out the different this spherical harmonics. I will show you one of the spherical harmonics to find out the one of the spherical harmonics corresponding to one particular value of L. Then we will just concentrate. Then we will just do it for the you can do it for the other cases. As okay, let me just start from the beginning again. As I was saying, if I have some function in spherical polar coordinates psi, which is a function of this r, theta, and phi. Okay, यहाँ से आप पूरा ध्यान रखिएगा. So I just separate, when I separate in three different, I write this as r as a function of r, theta as a function of theta, and this phi as a function of phi. Okay, now see this part, this is what we call as a radial part. ठीक है, and it depends upon the principal quantum number. This is a radial part or radial function. It depends upon the principal quantum number n and l. ठीक, n and principal quantum number l, and L is a magnetic quantum number, sorry, orbital quantum number. This is an orbital quantum number, and you know the quantum number, different quantum numbers आपने पढ़े हुए हैं. Okay, now this theta of theta जो आपका है, and this phi of phi, they are the angular parts. This is a radial part, they are angular parts. They are angular parts, and this theta will depend upon my L, yani orbital quantum number, and the magnetic quantum number, while this phi will depend only upon the magnetic quantum number m, right? So the product of this, actually the product of these theta and theta, that is what we call as a spherical harmonics, and I told you that is denoted by this psi I L m cos of theta. Okay, now we will try to find out the solution. Again, I said you the solution to this phi equation, that is phi m of phi m of phi, it's given by वहां पे जो constant है, it is actually equal to 1 by under root of 2 pi e to power I m phi. This is the solution to your phi differential equation, the differential equation containing the phi. And similarly, the solution to theta Lm, which is a function of L and M, which is a function of this theta, and it depends upon the orbital quantum number and the magnetic quantum number. It is always given by some constant, then under root of 2L plus 1 by 2, 2L plus 1 by 2, into L minus m factorial divided by L plus m factorial. This is the solution to that theta equation, L plus m factorial. Then we have PLM cos of theta. Okay, I'm just writing down the solution to that differential equation, to those equations directly. So we will, so this is actually a associated Legendre polynomial, जिसको हम बोलते हैं associated Legendre polynomial. Okay, now in order to find out the solution, and this epsilon जो यहाँ पे है, epsilon is some constant. Okay, and now you know that we can take the different values of L. This the जो part यहाँ पे है, जो आपके इसमें square root में है, you can easily find out the values corresponding equal this L. Now you know that for L equal to 0, M can take only one value. That is, for L is equal to 0, M is equal to 0, and for L is equal to 1, M can take values like -1, 0, and +1. For L is equal to 2, M can take values -2, -1, 0. 1 and 2, similarly, and so on and so forth. So we can correspond to different values of the L. I can have the different values of this magnetic quantum number. Okay, so let us try to find out these things, and so that we will find out this YLN, which is taken as a product of this theta and phi. So then I will just take the product of this particular function, this particular equation, and this product equation. But before that, let us try to find out these constant values as well as the this PL cos of theta. We are going to derive it from the things which you already know, like for example the constant epsilon. Let us try to find out the first of the constant epsilon. Okay, what could be the values of the epsilon? This epsilon is always equal to 1 when m is less or equal to 0, and corresponding to the m when m is 0 or m is less than 0, -1, -2, -3, this is always equal to 1. And this epsilon is equal to -1 raised to power m for m greater than 0. Okay? And you know that m is a magnetic quantum number, 1 raised to power m. Okay, for example, m is equal to 1. So what could be this epsilon equal to? It will be -1 raised to power 1, so it will be equal to -1. Similarly, when m is equal to 2, the value of this epsilon could be equal to -1 raised to power 2, that will be equal to +1. Similarly, for m equal to 3, it will be -1. For m equal to 4, it will be +1, so on and so forth. So this is, so we can substitute the value of this epsilon corresponding to different values of m, depending upon कि हम उस spherical harmonics में m का value क्या देंगे. This is one thing. Okay, now let us come back to this, the second part, जो Legendre polynomial है. Now we need to find out this PLM cos of theta. And if you remember, we have done this, the Legendre polynomial, associated Legendre polynomial, and you know how we define that Legendre polynomial. We are not going to find it again because we already have done it. That is a solution to your associated Legendre function. And okay, this is the first part, and the second thing is the Legendre polynomial. So you know that this PLM वहां पे हम x में हम इसको लिखें, PLM x is actually defined as 1 minus x square raised to power m by 2. Okay, then dm by dx raised to power m PL of x. This is as associated Legendre polynomial, and this PLX जो है, these are actually the Legendre polynomial. This is an associated Legendre polynomial. Also, you know that how we define this PL of x. PL of x, इसीलिए मैंने आपसे last time कहा था कि associated Legendre function और Legendre polynomial आप देख के आइएगा, because it will help you in this particular problem. It is always given by 1 by 2 raised to power L, then L factorial, dl by dx raised to power L, then x square minus 1 raised to power L. Okay, now I can use the different values of L. Let us try to find out solve this thing for the different values of the L. Okay, okay, suppose L is equal to 0. For L is equal to 0, okay, let me just write it. From this particular equation, first I will find PLX, then I will substitute in this equation to find the PLMX. Okay, see, so what is for L equal to 0? For L is equal to 0, this will be P0 of x. What will be this equal to? This will be P0 of x, and it will be equal to 1 by 2 raised power L, that is 2 raised power 0, that is 1, L 0 factorial, that is 1, this dl by dx, it will be 0, that is 1, that is this raised power 0, that is 1, then x square minus 1 raised power 0 x, so that is 1. So P0 of x will simply be equal to 1. Okay, now what is for L is equal to 1? For L is equal to 1, what is P1 of x? P1 of x, you have also obtained these Legendre, this Legendre polynomial जिनको हम बोलते हैं. P1 of x is equal to, now it will be 1 by 2 raised power 1 divided by 1 factorial, so it will be 1 by 2, then it will be d by dx of x square minus 1. Okay, so when you are going to do the differentiation, it will be 2x 2x 1 by 2 into 2x, so that will simply be equal to 2 and 2 will cancel, it will be simply equal to x. Similarly, for L is equal to 3, okay, this will be P, oh, sorry, L is equal to 2. For L is equal to 2, this P2 of x will now be equal to, shabash, it will be 1 by 2 raised power 2, that is 2 2s are 4 into 2 factorial, that is 2, then d2 by dx2, okay, then x square minus 1 into whole raised power 2. Okay, so then you are going to differentiate it again, this taking the second derivative and just taking this care of this particular term, the differential to this particular equation will be 3x square minus 1 divided by 2. These two you have already find out when we were talking about the Legendre polynomials. Okay, so if we find out the corresponding different values of L is equal to 1, L is equal to 0, 1 and 2. Similarly, you can find for L is equal to 3, 4, 5 and so forth. Okay, so now let us talk about, so when we find out this particular PL of x, we can find out this PLM of x. Okay, now coming back to this equation. Okay, now when L is equal to 0, as I said, this or magnetic quantum number can take only values m is equal to 0. So L is equal to 0, m is equal to 0. So this particular equation यहाँ पे क्या बन जाएगी, this PLM, it will be P00 of x will now be equal to, okay, minus 1 minus x square raised power m by 2, that is 0. So it will be 1, then this will be 1, then P0 of x. P0 of x किसके बराबर है आपका? P0 of x, that is equal to 1. So this PLMX will become simply 1. Okay. Similarly, now for L is equal to 1, for L is equal to 1, now M can take three different values. M can take three different values. M is equal to 0, minus 1 and plus 1. So let us try to when N is equal to 1 and M is equal to 0 case. Okay. So ये आपका क्या हो जाएगा? It will be P1 0 of x. P1 m is 0, P1 0 of x. Again, this will be 1 minus x raised power m by 2. This will be raised power 0, that is 1. This will be 0. Then PL, so it will be P1 of x. But P1 of x is equal to x. This. So this will be equal to, so P1 0 of x will be equal to x. Okay. So we see that if you compare these two equations, so we can conclude from these two equations that this PLM of x, PLM of x is always equal to PL of x if m is equal to 0. यानी अगर m 0 है, then PL, चाहे आप कोई सा भी वैल्यू ले लो, चाहे से कोई सा भी वैल्यू ले लो L के लिए, अगर P2 of 0, P3, P4, P5, P5, 0, this will always be equal to PL of x. So you don't need to find out for the other values. This is important point here. When m is equal to 0, PLMX is always equal to PL of x. So for example, I will tell you what will be the m is equal to 0, what will be the P30 of x. So P30 of x will simply be equal to this, P3x square minus 1 divided by 2. Fine. Similarly, so you can find out, we can find out the other values like, now as I said, this m can take the three different values. Okay. Now again, when L is equal to 1, m can also take the value plus 1. So for L is equal to 1 and m is equal to 1. So this will become now P11 of x. So later I will just change x to the cos of theta. So or you can just write it here, the cos of theta. So there is okay. So we have 1 minus x square raised to power, we have m by 2. M by 2, m is 1, so it will be 1 by 2, then dm, so dm is 1, so it will be d1 by dx raised power 1, then we have P L of x. Now L is 1, so it will be simply P1 of x. Okay. Now 1 minus x square raised to power 1 by 2, that is under root of 1 minus x square into d by dx of PLX. d by dx of PLX. PLX क्या है? ये sorry P1x क्या है आपका? P1x is x. So this will simply 1. So it will d1 by dx1 of P1x. M is equal to 1. P1 of x. P1 of x. P1 of x is x. Okay. So you can write down this as d by dx of x. So that will be equal to under root of 1 minus x square. Okay. Similarly, I can also have for this whatever we have L is equal to 1 and M can also take the value like -1. So it will be P1 -1 of x. असल में यहाँ पे हम ये under root of ये mod of M divided by 2 mod of M divided by 2 ये value लेते हैं. M not here, यहाँ पे है mod of M, यहाँ पे है mod of M. Original equation में, because we are going to take the positive values for the M only, right? Because here we cannot take the negative differentiation, the negative value for this, the derivative. Okay, so P1 of x, you can similarly find out the P1 -1 of x, whatever the value could be. Now I will substitute all the values, this Legendre polynomial and constant in the theta term, because we know that जो मैंने अभी लिखा था, this theta जो function है, which is a function of L and M of theta, it is always given by some epsilon under root of Shamash 2L plus 1 divided by 2 into L minus M factorial divided by L plus M factorial. Okay, then PLM cos of theta, this value. I have obtained the different values of this, so corresponding to, for we can find out the values for different values of this theta. So what is now theta? For example, for L is equal to 0, M is equal to 0. Okay, so this will be theta of 0 0 of theta, then it will be equal to epsilon. When L is equal to 0, abhi maine kaha tha, when L is equal to 0, M is always equal to 1. So this will be equal to 1 into under root of, okay, L is now 0, so it will be 2 into 0. This will be simply 1 by 2 into L minus M, that is L minus M, that is L is 0, 0 minus 0 factorial divided by 0 plus 0 factorial, so that is 1 simply, right? Then we have, so it will be 1 by 1 into bracket के बाहर now P00 of x. P00 of x मैंने अभी find किया है, P00 of x. So this will be equal to, this is 1 by under root of 2, 1 by under root of 2. P00 of x हमने find किया था, that is equal to 1. So that is equal to 1. So it will be simply 1 by under root of 2. 1 by under root of 2. Similarly, okay. So what could be the value of the spherical harmonics at 0 0? Therefore, spherical harmonic at this 0 0, that you know that is denoted by y0 of 0, which is a function of theta and phi. It will be equal to the product of theta Lm of theta and phi m of phi. Now at 0 0, it will be simply theta 0 0 of theta and phi 0 of phi. Now what is theta 0 of 0? We have find out that theta 0 of 0 is 1 by under root 2. Now phi of, you know that is equal to e raised to power I m phi, but 1 by under root of 2 pi, right? 1 by under root of 2 pi e raised to power I m, जो मैंने initially लिखा था. When m is equal to 0, it will be simply equal to m into 0, it will be e to power 0, that is 1, it will be 1 by under root of 2 pi. Okay, so then it will be equal to 1 by under root of 2 pi. So you can write down this as 1 by 2 root pi. 2 root pi, or sometimes some of the books have written it as 1 by under root of 4 pi. So that is one and the same thing. You can keep it like this or this, that is up to you. Okay, so we find out the value of the spherical harmonics for 0 0. Similarly, you can find out the values for the other harmonics, like you can find out the spherical harmonics y1 1 1, then also 1 0 0 0 हमने find किया है 1 0 0. You can find out for m equal to 2, so you can also 1 minus 1. So for this L equal to 1, m can take the values minus 1, 0 and 1. So you can find out these values, different values. Similarly, you can for example, if L is equal to 2, you know that L is equal to 2, m can take values from minus 2 to plus 2 through 0, plus 2 to 0 through 0, that is minus 2. So what will be the different harmonics then? The different harmonics in that case will be like y 2 minus 2, y2 minus 1, y2 0, then you can have y2 1 and y2 2, five values like this. So what you will do, so m ka epsilon ka value आपने पहले defined कर है. All you need to do is to find out this L into L plus 2L plus 1 by 2 L minus m factorial divided by m plus L plus m factorial, and this PLM cos of theta. This PLM cos of theta, these values you can find out. So this thing you will find out these and write down the spherical harmonics. At least to do write down the spherical harmonics for these three and these three. So this I'm giving you as an assignment to find out the spherical harmonics correspond to different values of the m and L. Okay. Just quickly, I am going to summarize it all these things. एक बार मैं सारी चीज को एक बार फिर से समराइज करूंगा, उसके बाद if you had some questions you can ask. Now as I was saying, the spherical harmonics actually started with the thing that they are actually used in the when we solve the hydrogen atom problem. So because the hydrogen atom has a spherical symmetry and we have the, for example, hydrogen atom में Helmholtz equation या Laplace equation या कोई भी problem हो जहाँ पे हमारे पास spherical symmetry involved हो, we can solve the particular function into, we can separate them into three parts: radial part, theta part, and the phi part. Now this is a radial part. For example, in case of a hydrogen atom, it depends upon the energy and volume, while these do not depend upon the energy and the potential. Now the product of these angular equation, that is theta and phi, we call them as a spherical harmonics, and it is denoted by YLM theta of phi, which is a product of this theta of theta, theta and this phi of phi. Yani this is the product of this theta solution of a theta equation and the phi equation. We call this as a spherical harmonic. Then I say that the solution to this this phi equation is given. It's simple because it is 1 by some under root of 2 pi e raised to power I m phi. Right, we have solved this particular problem. Just go through the separation of the variable technique jahan pe humne padha tha, and this theta equation, this is given by some constant epsilon, and then 2L plus 1 divided by 2 into L minus m factorial divided by L plus m factorial, and some Legendre polynomial PLM cos of theta. Yeah, x हम वहां पे लेते हैं. Now I simply replace x by cos of theta. Okay, now here simply this phi value you can obtain correspond. This phi actually depends upon the integer m only, which is a magnetic quantum number, whereas this theta depends upon both L orbital quantum number and the principal, this magnetic quantum number. So you can find out the corresponding different values of this phi 0, that is 1 by under root 2 pi. Similarly, when we have phi 1, it will be equal to now 1 by under root of 2 pi. It will be when m is equal to 1 e to power I phi. So you can write down this as 1 by under root 2 pi cos of phi plus iota sine of phi. Okay. Similarly, when phi is equal to 2, it will be 1 by under root 2 pi e to power 2 I m phi. So cos of 2 m pi plus I m. So you can find out the different values corresponding to the m. Similarly, I can find out the different values of this theta because it is a function of orbital quantum number. It depends upon the orbital quantum number, which is a function of theta, but it depends upon the orbital quantum number and the magnetic quantum number. So depending, as I said, this is the constant value epsilon, it depends upon the magnetic quantum number m. It is equal to -1 if m is less or equal to 0, and this will be equal to 1 minus 1 raised to power m for m greater than 0, right? वही मैंने कहा था. M less or equal to 0, and this will be equal to not -1, this is +1. It will be +1 for m less or equal to 0, and it will be if it is 0 it will be 1, and it will be -1 raised to power m for m greater than 0. So I can obtain the different values and depending upon कि हमें L के values क्या है. Similarly, this PLM cos of associated Legendre function, PLM cos of theta जो मैं कह रहा था, it is given defined as, we already have defined it when we were doing the associated Legendre function. It's given by some equation like okay, It's given by this PLM associated, yeah, PLM instead of cos of theta, you can also write it x. So 1 minus x square. Then I have this m by 2, then dm by dxm, and depending, it will all depend upon the PL of x. PL of x. So now this PL of x, then Legendre polynomial, we have also, it is given by 1 by 2 raised to power L factorial. Then dl by dx raised to power L, and then x square minus 1 raised to power L. Now obviously by substituting different values of L, we can obtain this Legendre polynomial, different values, like I can obtain p0 of x, p1 of x, p2 of x, so on and so forth. So once I obtain different values, I can just substitute the value of m. And now since this theta depends upon the m and the L, so you can take different values of L and m, like L is equal to 0. For L is equal to 0 case, m can take only one value, that is 0. But when L is equal to 1, your m can take the three values, m is equal to -1, 0 and +1. So you have to find out for all these three this PL0. So you have to find out this for L is equal to 1, P0 of x, एक तो ये आपका है, you have to find out P -1 0, and then P1 of 0, P1 of 1, and P1 of -1 of x. You have to find out all these values. From that case, you can find out. So this for L equal to 1, we can have the spherical harmonic, three different spherical harmonics. This YLM जो ये थे, YLM theta of phi. So I will have for L equal to 1, M is equal to 0, 1. For L is equal to 1, M can be -1, and this equal to 1 and 1. So these three different harmonics. One for the one case, for the one case, that is L is equal to 0, M is equal to 0. I find out the spherical harmonics, and I showed you. You can just proceed the same way to find out the spherical harmonics for these values for L equal to 0, and this I am giving it as an assignment for L is equal to 1 and for L is equal to 2. Now for L is equal to 1 case, M can take values -1, 0 and +1. For L is equal to 2, M can take values -2, -1, 0, 1 and 2. Okay, you just find out the spherical harmonics for these conditions. That is all about the spherical harmonics. Later you are going to apply it in when we will do the hydrogen atom problem in quantum mechanics. Now it will help you in solving the hydrogen atom problem there. But go through it thoroughly, find out these values, so that you will get a proper understanding. Once you will do it yourself, you will understand the things better. Okay, this I am giving you as an assignment. You just follow all these things. I can ask any one of you in the next lecture to find what was the value to the particular this part. Okay. Okay, so with that, I'm going to, you do join for another meeting. एक बार फिर से आप join करिएगा, because we will discuss some